Hello, everyone. We're going to talk about PolarFire SoCs memory subsystem today. PolarFire SoCs and FPGA from MICROCHIP. And about me, my name is Tim Morin. I'm responsible for helping to define new products for the FPGA business unit and bring them to market. Part of a broad team that does that. 30 years of experience in engineering and marketing. I've worked at numerous companies in positions of each in those companies, and I'm very glad to be here today. Thank you very much for spending some time. So we'll do a quick recap of PolarFire SoC. We'll go into some of the details of the L1 memory subsystem and the L2 memory subsystem, and we'll just wrap up. PolarFire SoC is an SoC FPGA, and it's built on top of our low power 28 nanometer non-volatile memory technology. Unlike other FPGAs in the market, it powers up instantly. That's due to the flash programming or non-volatile programming. You program the part and it powers up instantly. It can power up in less than 10 milliseconds. It consists of a 5-core processor subsystem, a monitor core, 4 application cores, rich I/O out into the right here. Certain devices have a side channel resistant crypto accelerator. Side channel resistance is kind of necessary if you want to do any kind of real security. It's one thing to have an AES core that implements an AES function, but if it's not side channel resistant, then somebody can steal the keys that the AES core is using to encrypt or decrypt traffic just by measuring the power supply of the device. So security is more than just meeting a standard. It's got 2 GigE Ethernet max, full featured, multimedia card, CAN, quad SPI, SPI, UART, etc. There's extensive debug capabilities built into this chip. The processors have instruction trace. There's an AXI bus monitor. The AXI bus monitor can monitor traffic into the L2 memory subsystem, so I can monitor what address a master wrote to, so I can monitor all the masters writing into the L2 memory subsystem. It has runtime filtering capabilities, so I can filter on a particular master or address range. And I can also monitor the AXI bus traffic coming in and out of the switch. That switch has built-in memory protection. The memory protection is a little bit different than an MMU or an MPU you see in a micro. It allows or disallows certain masters in the I/O space and the FPGA space to get access to the L2 memory subsystem or the DDR memory controller. And there's a quality of service capability in this central switch. For each path, you can define bandwidth and latency. There's a bandwidth regulator, and there's a priority latency arbitration scheme built into each path. The bandwidth regulator effectively, allows a certain number of clock transactions to pass. So you can tune, the performance going in and out of the processor subsystem into the FPGA fabric. We have a secure boot capability. We've got 2 methods of secure boot. And we deliver the device with something called Heart Software Services, which helps set up and initialize the device and get you going. And it also has 128 KB boot flash. So your 0-stage bootloader goes here, and you can change it. 2 interrupt controllers, a platform interrupt controller. So all interrupts in the system can get steered to here and then steered to the core of your choice. The local interrupt controller, each core has a set amount of local interrupts, and those are all sourced from the FPGA fabric. The FPGA is built on top of PolarFire FPGA technology. So if you're familiar with PolarFire FPGAs, then all the parameters are exactly the same. All the electrical characteristics, all the performance and power numbers are all the same. We effectively take a PolarFire FPGA, notch out a corner of it, and drop in a processor subsystem. There is dedicated I/O over here associated with the processor subsystem. And everything in the processor subsystem can be powered up and run independently of the FPGA fabric. Now, the FPGA fabric will be powered up in that case, but the FPGA fabric can be blank. So you can actually run Linux out of this orange block without ever touching any of the FPGA development tools. So it's really kind of handy for Linux application developers to be able out of the box, just start writing code and porting applications to this architecture without having to worry about the nuances of placing and routing and synthesizing and timing constraints that you have to do for an SoC FPGA. So that's kind of like an overview of the block diagram, kind of orient to you as to chip level architecture. But if there's one thing that is probably our biggest differentiator in the market, and why we've made this product, it is the lowest power mid-range SoC FPGA in the market, and we benchmark it against our competitors, dual Cortex A9 chips and dual Cortex A53 chips. The horizontal axis is milliwatts, and the vertical axis is core marks. You can see, the static power contribution and the technology choices that each supplier makes. Our static power is running roughly at 700 milliwatts, and our competitors at 1.4 over 1.5 and 2.75 watts. Now, this benchmark is really a benchmark of the processor subsystem. There's nothing running in the FPGA fabric, but the static power contribution of the FPGA fabric is being added into this. It's a fair benchmark of what an application would see. We top out at around 8,000 core marks at roughly 1.4, 1.3 milliwatts. Our competitors are anywhere from 2 over 2.5, 2.25 to 3.25 watts. So anywhere from 2x to 3x the power of PolarFire, and that enables you to change how you construct things. You might be able to get rid of fans in your system. We have a lot of customers doing that today with PolarFire. If you have industrial IoT switches or anything that goes outside, and it's a thermally constrained environment, and if you can design a system without a fan, then you can design a system that can last longer without a fan failing and having to roll, a van or swap out equipment. So we don't like fans here in the FPGA business unit, and we're very keen on delivering power efficient mid-range compute platforms to the market. Now, the L1 memory subsystem, monitor core, application cores, both have instruction cache, but they also can be configured as tightly integrated memory. The monitor core has an additional scratch pad, and the application core has a data cache. Now, the tightly integrated memory is obviously used for things like interrupt service routines, or I've got some kind of compute algorithm and I've got some code that's pretty tight, and it will fit in 24 kbytes here or 8 kbytes up here, and it'll just scream. It'll run at processor speed. Okay, and to use the tightly integrated memory, it's relatively simple. Each tightly integrated memory has a separate address region that it is addressable at. Here, the E51, which is the monitor core, is addressable at 0180000, and the U54s likewise are at very specific addresses. And to convert that cache to a local memory, all I have to do is write to it, and writing to it by filling up code, and it becomes a local memory. And I can deallocate the local memory back into the cache just by writing to the last address in the address range for that particular TIM. So it's a very flexible L1 memory system that you can actually change dynamically. Okay. Now, the L2 memory subsystem is relatively large. I mean, you don't see 2 megabytes of L2 on SoC FPGAs at 28 nanometer node. I think our competitors have 512 kbytes. And I think you'll see why we did this in a minute. So there's 16 ways, 128 kbytes per way. That's a very important number to remember. There's 4 physical banks. And each cache line is 64 bytes. And there's 3 operating modes: cache with write back, which is normally what an L2 memory subsystem does, but it can also perform this loosely integrated memory function, which we'll talk about in a second. And it can also perform as a scratchpad memory. Excuse me. Now, it can perform these 3 functions all simultaneously. Now, the loosely integrated memory is deterministic memory behavior, equivalent to a cache hit, an L2 cache hit, with no penalties in terms of a cache miss. And because the L2 memory is arranged in 4 or 512 bytes, we've arranged the priority of the limb or to have priority over a cache access within that same physical memory. So the limb has priority over the cache, and the reason we did that is because we have customers that want to run a real-time operating system and a rich operating system side by side on the same chip. But anytime you want a real-time operating system, you want determinism, and hence the priority over the cache. So we can throttle Linux a little bit and nobody will notice the difference. But if you throttle a real-time operating system, something's probably going to fail. At power up, the entire L2 memory subsystem, except for one way, is a cache. And unlike the L1 memory subsystem, the L2 memory subsystem configuration is kind of like a static thing. You do it on power up, and then you don't change it. It's not really designed to be dynamic. And to address the limb, you just address this address. And this shows 2 examples of default power up behavior. And then we got 1, 2, 3, 4, 5, 6 cache ways defined, and the rest as a limb. Now, the L2 can also operate as a scratch pad, and it's addressable at a specific address. Okay. The difference between the loosely integrated memory and a scratch pad memory is the scratch pad memory is cacheable in the L1 data caches. So it acts as a data buffer memory that's coherent across all cores. So it can be used to store, inter-processor communication messages is the ideal place for an L2 scratch pad. Now, there's no copies in DDR, and evictions result in loss of data. And you can use way masking to prevent that eviction. Okay. Now, to configure the L2 subsystem, there's 3 registers essentially. The way mask registers, there's actually more, but conceptually there's 3 things you got to keep in mind. The way enable register, very simple. Determine how many L2 ways are going to be cached, and the rest would become limbs. The way mask register, which defines whether a master has eviction rights or not. If you don't want a master to evict a way, then you set that to a 0. And there's also flush registers to flush the cache as needed. The L2 has 15 masters getting access to it. DMA, the FPGA has 4 ports that you can that can be accessed into the L2, and each core has 2 data and instruction path. Okay. Now, here's a simple example. I want a 2 megabyte cache, so I just programmed the way enable to 15, and all the cache ways, all the ways are enrolled as a cache. If I want to reserve some cache space for a loosely integrated memory, in this example, 384 kbytes, then I just program this register to be a 12. I make sure all my way mask registers are 1. And then I have these cache ways available as cache, and all masters in the system have access rights to evict. And in this example, I'm going to actually borrow some of the cache ways and make a scratch pad out of them. I don't change the way enable register, but I change the way mask registers to zeros so that these masters can evict from these cache ways, effectively turning it into a scratch pad. Okay. And you can see with the 15 masters, each master having its own way mask register, I can create quite complicated arrangements of caches, loosely integrated memories, and scratch pad memories on a per master basis with the granularity of a single cache way, 128 kbytes. All right. Excuse me. So, after the L2, obviously, you go off chip to the physical memory. And there's an integrated hardened DDR controller that can support LPDDR4, DDR4, LPDDR3, DDR3, up to 1.6 gig data rates. It's 2-ported. There's clock domain crossing circuitry built in to accommodate, the various different rates that an FPGA or a CPU could run at. There's a command queue depth of 8. There's a priority encoder built in, 8 levels deep. If the priority is equal, then arbitration is on a round robin basis. And if I wanted to guarantee some bandwidth, if I want the FPGA to carve out some bandwidth of the DDR, I can do that by using some programmable timeouts. In that particular case, you might have virtualized, not all of the physical memory, maybe 3/4 of the physical memory, and reserved 1/4 of it for the FPGA, and you want to make sure that FPGA gets access to it. So you can use the programmable timeout to guarantee a certain amount of bandwidth. Now, this shows, another view of the block diagram. The monitor cores here, the application cores here. We have DMA. These are the 4 ports from the FPGA. And here's a coherent switch into the L2 cache, accessing the DDR memory through this segment 0 over here. We have also other DMA capable peripherals here in the IO space, and anything you want to put in here can be a master on this coherent switch. And to access the DDR memory, I can do it one of 2 ways. I can do it coherently through this path here, or I can do it to a separately carved out physical address space through this path here. The WCB is a write combining buffer, and that's designed to aggregate single cycle types of transactions into a local buffer before bursting it out into the DDR to save on memory bandwidth cycles. So to quickly summarize, PolarFire SoC is market leading in its power efficiency. It enables new applications. We have very small form factor packages, 11 by 11, 11 by 14, 16 by 16. You can get a lot of compute density per millimeter squared at very low power with PolarFire SoC. It is, the world's only SoC FPGA with a hard 5-core RISC-V processor subsystem. Okay, so it's designed to work out of the box, with Linux, with real-time operating systems, and both at the same time. And the whole memory subsystem is very flexible in its partitioning and its performance capabilities for various types of applications, mixed criticality, or just tuning your application to extract that last bit of efficiency at a particular power envelope for your application. So I'm glad you guys spent some time with me today. If you want to learn more about PolarFire SoC, just use your favorite search engine for PolarFire SoC. You'll land up on our pages. I think we have some videos here in our virtual booth. One is on the Icicle kit that's going on sale soon. It's going to be very, very popular. So reserve yours today. And thank you very much. And I hope you have a good show. Thank you.